Okay, so the normal force, up until this point, we've understood the normal force to go straight up in the air. Okay, that's not necessarily the case. The normal force is the force that's exerted by the surface on the object. So, if I've got an object on an incline, my normal force no longer just goes straight up into the air. Okay, that's not what it looks like. Our normal force goes perpendicular to the surface. Okay, so here is my new normal force. So why does that look problematic?
Because it's not straight up and down.
Not straight up and down, right? So if we use our normal axes, that means we're dealing with a lot of components, right? We're breaking down that x and that y. That means angles, that's right. So there's going to be a little bit of a fix for that, and I'll show you here in a second. Okay, the normal force goes perpendicular to the surface does not mean it necessarily goes straight up in the air. Okay? The gravitational force, however, does not go perpendicular to the surface. The gravitational force always pulls us where?
Down.
Straight down. Okay, it always pulls it straight down. Okay, so now if I have my object on an incline, I've got my normal force going perpendicular to the surface, and I've got my gravitational force going straight down. Okay, do we see the difference there? So are these two going to be equal to each other? No, right? They aren't completely opposite. One of those is going to have to be broken into components, into its x, into its y component. Okay, one of them. So to fix this problem of having all of these components, we're going to tilt our axes. So here's my incline. Now here is my x and my y axes, right? This would be the positive direction, negative direction, negative direction. Do we see what we did there? We just kind of shifted that. So that helps us not have to break every single thing into components. Okay, it makes a big difference. So when we deal with things on an incline, we kind of just shift our view a little bit so that we can see these axes a little bit clearer. Okay, and the reason for that is so we don't have to deal with quite as many components. We're not breaking down quite as many vectors. Because if I look at my box here, I've got a normal force, I've got the gravitational force. Let's say that I am pushing the box, down the incline, so I've got some applied force, and let's say there's some friction, so I have a frictional force. So which of these forces is the one that has components now? Which is the most problematic?
The gravity.
Gravity, right? So here's Fg, and we know our axes look like this. Okay, so the green lines are the axes. So now the gravitational force is one that has to have components. The normal force is still purely vertical. The applied forces and the frictional forces are purely horizontal. Okay, so now the gravitational force is the only one that would require components. Does that make sense?
Yes.
Okay, so we're going to look at how to work with these gravitational components. All right, since Fg points straight down, we have to work with components of the gravitational force, okay? And let me draw this out and then we'll label what this means. Okay, so I've got a box with a gravitational force that is pulling it straight down. Okay? Since our axes look something like this, okay, remember we need our components to touch one of the axes. Okay, we always just make it touch that vertical axis. Drawing this gravity triangle is extremely important. We need to make sure that the right angle is opposite of that hypotenuse. The gravitational force is always going to be the hypotenuse of that triangle. Okay? Gravitational force is always the hypotenuse. Then we're going to build the components from there. Okay, so building your components to look like this is not correct. Okay, so going here and then up, trying to make the right angle right there, that's no good. Okay, the right angle has to be opposite of our hypotenuse. Does that make sense? Okay. So, now let's talk about labeling these sides. This horizontal component of our gravitational force is called F parallel. That's not F11. Okay, it's called F parallel. And these are two little parallel lines. That's why that's labeled like that. Okay, F parallel. Why do you think this component might be called F parallel?
It's parallel to the x-axis.
It's parallel, exactly. It's parallel to the surface of the incline. Okay, or to the x-axis. Very good. Uh-huh. Oh, I thought you had a question.
No.
Okay.
Just celebrating.
Okay. And then our vertical component we call the normal force. Okay, and why do you think that might be the case?
Because it's still going upward.
Yeah, these two forces are equal to each other. The normal force can be found from the y component of the gravitational force. So this normal force above the x-axis is equal to this right here. Okay, that's assuming the box is sitting on the ramp. If it's lifted off the ramp, then we got problems. Okay, if it's on the ramp or on the incline, this normal force that we get from this triangle is going to be equal to this normal force. Does that make sense? Okay, so we're good with the labels on that gravity triangle now? Okay, this is true for every one. If I have an angle that goes right in here, okay, let's say 30 degrees, my parallel force is sine or cosine? Sine, because it is opposite. Normal force is cosine. That is a rule that you can memorize. Okay, for these gravity triangles, parallel should always be sine and normal force should always be cosine. Okay, you don't have to memorize it. It's going to show in your triangle every time, but you can remember that. So parallel is going to use sine, normal force is going to use cosine. Okay, so we're just going to go ahead and start with a practice problem here. Again, this is one of those ones where I'm going to walk you kind of through every step, but you can understand our overall goal is to find the acceleration of the box as it slides down the incline. Okay, so we want to know the acceleration of that object. Okay, does this problem tell us anything about friction?
It says with friction.
Frictionless. Okay, so we don't include friction. Okay, so we've got these forces. This one would be labeled with what?
FN.
Normal force, good. And this one would be FG. Okay, so now I need to break that gravitational force into its components. Okay, and the bottom or horizontal component would be called parallel, and this would be called normal. Okay, so here's the last little thing I wanted to explain to you about this diagram that goes with it. This 30 degrees, so that means my incline is sitting at a 30-degree angle. Okay, that's what that means. The incline itself is sitting at a 30-degree angle. That angle of our incline fits right in here in our gravity triangle. Okay, so it fits right into this little crevice right here, okay, that 30 degrees. So whatever angle your incline is sitting at, that fits into your gravity triangle. Okay, so 30 degrees. Okay? So there's a couple things that we want to look at. Our overall goal is to find the acceleration. Do you think we're looking at horizontal acceleration or vertical acceleration? Horizontal, right? Because we've shifted our axes to understand this is the positive direction and this is the negative direction. Why would we choose the positive direction to be down the incline? Okay, it is east. Why else? What if I drew my incline like this?
Because it's going to the clock.
Sort of, okay. Where do things mostly go on an incline? Do they go up or go down?
Down.
Down. That's why we choose it to be the positive direction. Okay. If you were pushing something up an incline, you could change up to be the positive direction. Okay, but most of the time we think downward because things slide down the incline. All right, so our overall goal here is going to be a horizontal acceleration. So let's work on breaking down a few of these things to get to that point, okay? First thing that we need to do is solve for the force due to gravity, right? We don't even know the hypotenuse of that triangle. How do we solve for FG? Yeah, FG is still gravitational force, which is mass times 9.8. Okay, that should be something that is 100% you know every single time. It's mass times 9.8. Okay, that should be something that you feel really comfortable with by now. Okay, so FG is equal to 10 times 9.8, which means the hypotenuse of that is 98 newtons. Okay, so now we need to basically solve for the normal force and the parallel force. Okay, if I want to solve for the normal force, I'm going to use sine or cosine. Cosine, because the normal force right here is adjacent to that 30 degrees. So I would use 98 times cosine of 30 degrees. Make sure that your calculator is in degrees, not radians. To find F parallel, we would take the hypotenuse times sine of 30 because that parallel component is opposite of my 30-degree angle. 49. Okay, 49 newtons. So we've solved for the force due to gravity, we've solved for the normal force and the parallel. We need to find the acceleration of the box. So how do we go about doing that? That's the way to start it. F net equals positive forces minus negative, right?
Yeah.
We're still using that application. Positive forces minus negative. What's our positive force here? Positive horizontal force.
Fn.
Fn is a horizontal force.
Nope.
F parallel. Even though it's kind of written off the axes a little bit, it's still pulling it down the incline. That's what gravity is doing, right? The horizontal component of that is pulling it down the incline. So F parallel is our positive horizontal force. Is there anything acting against that?
No.
No friction, no nothing. Okay? So that's how we're going to set that up. What can we substitute for F net? Mass times acceleration. So we'd say 10 times A equals 49 minus 0. Okay, and you can drop that minus 0 if you'd like. Okay, which means A is equal to 4.9. So did we have to solve for the normal force here? Did we need it? No, we didn't. Okay? We might need it if we have friction, though, right? Because what's the equation for friction? That's right, the coefficient of friction times the normal force. So there is going to be times where you need to solve for both of those. All right, how do we feel about inclines? Okay so far? All right, that's good. Good, good.
I don't really understand what was the equation for friction?
If we had friction that was being applied here, okay, let me just put it in a different color so we can see that. If we had friction, we would say minus the frictional force instead of minus 0, right? And the frictional force is equal to the coefficient times the normal force. So in that case, we would have to find the normal force when we plug it in there. Does that make sense? Okay. Let's try this one. If you're not writing down the whole problem, that's fine. I at least want you to start writing down that free body diagram or drawing that diagram of the incline. Okay? We'll talk about what that 8.45 meters means here in just a second. Because it does have something to do with it. That's right. Yeah, that's right. Okay, so looking at our problem here, we need to label our components, so force parallel and the normal force. It says it's frictionless, so we've got nothing going against it there. We want to know how long will it take. So that means overall, what's our goal here? Yeah, which is time, right? We need to find time. Okay, that's what I was looking for there. We need time. But looking at our kinematics equations, which you might need right now, so let's get those out. Kinematics equations. Got to memorize, that's fine. Okay. Looking at these equations, we know that the distance this box is going to travel is 8.45 meters. So our distance final is 8.45. What's that make our distance initial? 0. Okay. And so looking at that equation, don't we think we probably need a few more things? Yeah. Distance initial is 0 because it's starting at the top of the box. That's where we're going to consider our starting point. Velocity. Initial or final velocity? Okay. Initial velocity is probably what? 0. Okay. It starts from rest. Yeah.
Could we switch the final and initial displacement?
You could. Because in the equation that we're going to need to use, right, df equals di plus vit 1/2 at squared, you're just going to subtract over that initial displacement anyway. Yeah.
I figured I would do it because I don't like this test.
That's okay.
From
Sorry.
the final, will all the equations be out?
Yes. All right, so basically what I'm getting at here is to solve our kinematics equations, we have to have acceleration. And we don't have that yet. So we're going to use basically those same principles that we did in the last problem to solve for acceleration, and then we plug it into a kinematics equation. So we have to double dip here a little bit. Okay? So let's solve for our components first. This is 33.3 degrees. Do we need the normal force in this problem?
Yeah,
No friction. Okay? It's never going to hurt you to solve for it. You just don't need to. Okay? So let's solve for the parallel force. Okay? What is Fg equal to? Yeah, it's already 466. Why is that the case? Weight. Okay, this is really, really important because several of you get mixed up on this. If it's already in newtons, that means they already took it times 9.8 for you. You do not need to do it again. Kilograms is mass, which means you take mass times 9.8. If it's in newtons, it's already a force, which means it's already your force due to gravity. Does that make sense? Give me like a yes or a no for that. Okay, because a lot of you are still taking these numbers times 9.8, which throws your whole answer off by an order of 10, basically. Okay, so please make sure that you're being careful there. So 466 is our hypotenuse. We'll take our hypotenuse times sine of 33.3. Okay, and I came, yeah, what'd you get, Eric?
255.84.
We'll keep it at 8, but yeah, good. 255.8. Are we all getting that to come out okay? Okay. So that is our parallel force. Let's set up now our net force equation, since that's our only horizontal force that we have. Okay, F net equals F parallel minus anything? No. No friction, nothing else opposing that motion. Okay, so now we need to take mass times acceleration equals parallel force minus 0. What do we know our mass? What's our mass?
466.
Divided by 9.8. Why do we have to divide that by 9.8? Yeah, that's where it gets tricky. You guys try to either multiply by 9.8 then use that for the mass, which that's like double dipping wrong. Okay, it's already in newtons, which means they took the mass times 9.8 for you. So to get the mass, you need to take 466 equals m times 9.8. Right, so we're going to divide by 9.8. Divide by 9.8 to get our mass. I need like a firm yes or no if we understand where that mass came from and we understand how to get to that point. Because if you don't, I need you to ask questions because that's something that we have to be good with. Okay? If it's in newtons, it's already FG. If it's in kilograms, that's your mass. Okay? So remember, mass always needs to be kilograms. Okay? Mass is not in newtons. All right, so we're going to take 47.6 times A equals 255.8, and we get our acceleration equal to about 5.37. Oh, 5.38. Either way you round, that's fine. Okay, so now we've got our acceleration. What kinematics equation can we use? I would agree. The second one, df equals di plus vit plus 1/2 at squared. Do we have to use the quadratic? Not when vi is 0. So we got lucky there. Okay, so you would say 8.45 equals 0 plus 1/2 5.37 times t squared. Okay, acceleration here is positive because it's going in the positive direction. So divide by 1/2, divide by 5.37, or multiply those first, then divide. And then square root that. Okay. What did we get our time to come out at? It's still called a frictional force.
No, but I'm going to the right since the friction.
Yeah, okay, let's look at the diagram. Here's my object. For some reason, it's always a blue box. Okay. So we've got gravitational force, normal force, frictional force. But we don't have any other applied. We're not pushing it down. The positive horizontal force is the parallel force. So it's gravity that's pulling it down the incline. Okay, the normal force of the gravitational component is keeping it on the incline. The parallel component of the gravitational force is pulling it down the incline. Okay, so they do two different jobs. All right, so what should be our first kind of mission here?
To find the
F and F parallel.
Yeah, let's remember our overall goal is to find the acceleration. I clicked you through the questions, but I just decided not to do that right now. Okay, so our overall goal is to find the horizontal acceleration here. Okay, just keep that in mind. So I'm sorry, what did you tell me the first step needed to be? Find the force of gravity, good, and then we can start looking at our triangle. Okay, so 50-degree incline goes right in here into our gravity triangle. Okay, 50 degrees goes there. What do we know about FG? What's that equal to? 20 times 9.8, which gives us about
196.
196. Okay, so that's the hypotenuse of our gravity triangle. 196. Are we going to need both the normal force and the parallel force here?
Yes.
Yes, we will, because friction requires the normal force. So let's start looking at those. Hold on just 1 second, please. Thank you. It's okay. 196 times cosine. I just want to make sure everybody has time to get there.
It's 150.14.
Okay, and do we have a normal force component yet?
125.99. Or you could just take that.
Let's just round that up to 126. Next step's going to be to set up our net force equation, which is positive forces minus negative. Are we going to want to look at our horizontal forces or our vertical forces?
horizontal
Horizontal, okay? And let's see, how many horizontal forces do we have?
2.
1, 2. Okay, one in the positive direction, one in the negative direction. So we'd say parallel force minus frictional force. Okay, you can solve for the frictional force outside of that net force equation, then plug it in if you want, or you can just do it all in one equation. It does not make a difference. Okay, so let's substitute mass times acceleration equals the parallel force, which is 150.14, minus the frictional force, which is the coefficient times the normal force.
Yes.
Okay, and so if I put the numbers in that go with that, we would say 0.4 times 126.
And you got 0.4 from...
The coefficient of friction, it's given right here.
Oh, okay.
Okay.
What have we done?
I'll be like 90...
I got 1.9.
987.
It's about 5. What level is that?
I got it more accurate. No, I just bounded. Which means less accuracy.
Here. Oops.
Oh, no. Sorry.